Okay, let's get started. Hello, good morning, everyone. Welcome to the University of Washington ECE Department Colloquium. Today, it gives me a great pleasure to introduce our colloquium speaker, Dr. Brian Bennett from Office of Naval Research. He's gonna give us talk about the century of science for Navy research. Dr. Bennett received his bachelor and master degree from MIT. He then served as an officer in US Air Force, conducting research in solid-state electronics. Then he returned to MIT to receive his PhD degree in material science and engineering. From 1992 to 2014, he was at the Naval Research Lab in Washington, DC. His research has been focusing on molecular beam epitaxial and application of antimonide and arsenide semiconductor heterostructures. And he also served the head of the nanotechnology section, where he leads 12 PhD scientists. Since 2014, he has been at the Office of Naval Research, where he is a program manager for electromagnetic materials. And Dr. Bennett is a fellow of American Physical Society. I should disclose that Dr. Bennett also generally supports my research and Professor Akama Junda's research. Okay, without further ado, we can give Dr. Bennett a virtual welcome, and let's listen to his talk. Thank you.
Okay, well, thank you for having me today. Sorry it couldn't be in person, but I think this will be good as well. So let me start, for those of you who may not know, explain what the difference is between these two organizations where I've spent most of my career. So the Naval Research Laboratory is a laboratory, or you could think of it as a couple hundred laboratories, located mostly in Washington, DC. And there people do both basic and applied research of interest to the Navy. On the other hand, the Office of Naval Research is only about 10 miles away in Arlington, Virginia, but it's a funding agency. So in some ways similar to the National Science Foundation, we fund universities, but we also fund small companies, as well as the large defense contractors, companies like Lockheed Martin and Northrop Grumman. And but again, on both basic work at universities and more applied work at the companies. So for the most part, people at ONR don't do research themselves, and for the most part, people at NRL don't fund research elsewhere. But there's still a lot of overlap between the two organizations in terms of working in some of the same technologies and some of the same missions. So today I'm going to start talking a little bit about what was going on in US science and technology in the early 20th century and how that led to the creation of NRL in 1923. And I'll talk a little about some radar research that went on at NRL in the 1930s. And then I'll spend quite a bit of time on the Second World War, and especially the role of universities in scientific research for the war effort, and talk about how that then led to the creation of ONR in 1946. And it's a few R&D highlights from the post-war period, and then I'll say a little bit about NRL and ONR today. Now, based on my education and background, I think you could classify me either as a scientist or an engineer. I've always sort of been on the borderline of those two fields. And in my current job, you could call me a bureaucrat, and that's okay. But one thing I'm definitely not is a professional historian. There are, people who devote their careers to things like the history of science, the role of the federal government in promoting technology. They go through and they, interview famous scientists and engineers. They go through old laboratory notebooks. They write books and papers about these events. And I haven't done any of that, but I've actually read a number of these books and these historians have written, and as well as a number of papers that were written during some of the times I'll be talking about. And the more I got into it, the more I found it to be very interesting. So that's why I decided to put this talk together. So I'm going to start in 1915, so a little over 100 years ago. Woodrow Wilson was president of the United States. And the US had just over 100 million people, which was a little bit over 5% of the world's population. Today, I guess we're around 330 million, and we're a little bit under 5% of the world's population. Most Americans were literate, but only 14% had a high school diploma. Only about 3% had a college degree. And that would be around the year where most demographers would say the US went from being a primarily rural country to a primarily urban country. And that's a transition, by the way, that only happened about a decade ago in China. Now, on the science and technology side, the Nobel Prize in Chemistry that year was awarded for research in chlorophyll and plant color. In physics, it went to the father-son team of William Bragg's for analysis of crystal structure by X-ray diffraction. I think in my scientific career, I probably used Bragg's law more than anything else because I was frequently trying to measure lattice spacings and compositions of compound semiconductors. Also in 1915, Einstein's theory of general relativity was published. Now on the technology side, that was the first coast-to-coast long-distance phone call was made by Alexander Graham Bell, and it was in part made possible by a fairly newly invented vacuum tube amplifier. The 1 millionth Ford rolled off the assembly line, and radios had been invented in 1915, but they were not commercially available for use at home, and we'll come back to that in a few slides. Now, there was also a war was raging in Europe. What they then called the Great War, which we now call the First World War, had started the year before in Europe in 1914. In 1915, the US was still officially neutral in that war. And that war saw the first widespread use of tanks, submarines, airplanes, as well as poisonous gas. And by far the most famous inventor in the world at this time was Thomas Edison. He had a lot of inventions which had touched the lives of people all over the world. Well, one was a phonograph. Another was a light bulb. Now, he didn't actually invent the incandescent bulb, but he made engineering improvements that increased the lifetime from seconds to many hours, so made it actually useful. Now, as he invented a lot of these electrical devices, there was a problem that the people didn't have electrical power in their house. So in the late 1800s, he actually developed the first power station in Manhattan, in New York City. And by 1915, about 40% of the homes in the US had electricity. And once they created that power station and hooked up homes to it, they had a problem is they didn't know how to charge people. They didn't know how much power each house was using. So Edison, being the great inventor he was, he came up with a solution. He calls it the Weber meter. It's just a solution of zinc sulfate and 2 zinc electrodes. The current, as it comes into your house, would pass through this circuit, and it would transfer zinc from one electrode to the other. And then the reader would come by periodically, take out your electrode and weigh it. And based on that, they would determine how much power you'd used during that period. And this was used for a number of years throughout the world until some better techniques were developed to meter power. He also greatly improved batteries. Even then, he and others were talking about a practical all-electric car. And of course, that didn't really happen until recent years. But the batteries he did make then were used in cars with internal combustion engines, as well as submarines and a lot of other applications. And not every invention he had really worked out. He had a patent on talking dolls. The problem was back then the voice reproduction was very poor. It was very screechy, tended to scare any small children. And they weren't very durable. Once the kids dropped the dolls, they stopped working. So that was one invention I don't think he made any money off of. But he was quite a prolific inventor. And in all, he had 1,093 US patents. And until just a few years ago, that was the record for anybody in the United States. And one thing he didn't patent, but you could argue that he invented, was the Industrial Research Laboratory. And here I show, this is his lab in Menlo Park, New Jersey from 1876 to 87, and then they actually moved to a larger facility after that. And you can see a photograph of the men working there, one of the laboratories, and then as well as an artist's rendition of what went on in this laboratory. Some would say this really wasn't a research laboratory. You think about a place like the University of Washington, where you have a number of PIs working on their own projects independently. That's not what was going on here. Here, there are teams of people that they were all working for Edison on his inventions. That's how he got to over 1,000 inventions. We had teams of people working on these. So some people would say better to call this an invention factory, not a research laboratory. But if you don't think of that as the first research lab, you might think of the GE lab in Schenectady, New York. Now, Edison actually owned a pretty big chunk of GE at this time, but he didn't control this lab to the extent he controlled his own laboratory. And this lab was created in 1900. Elihu Thomson was one of the founders and later served as president of MIT. When it was founded, he said, "A company as large as GE should not fail to continue investing and developing in new fields. There should, in fact, be a research laboratory for commercial applications of these principles and even for discovery of these principles." So he's calling for both basic and applied work. This is Professor Langmuir's lab there. And here's some work on some high temperature work, not so different than furnaces I used in my career, as well as some low temperature work in liquid nitrogen. So the lab was created in 1900. I pulled these from a paper in 1929 that was talking about the early years of the laboratory. So in addition to that lab in 1900, it's a few years earlier, Alexander Graham Bell's laboratory in Washington, D.C. in Georgetown. That's a fairly recent photograph. The building still exists today. It's a National Historic Landmark. And when he actually went to lay the cornerstone for the lab, he gave the honor to a 13-year-old acquaintance of his who was Helen Keller. So that was 1893, and then another was Westinghouse in 1916. So the early part of the 20th century, you're starting to have the first of these research laboratories for the companies. And there were also big changes in higher education. In fact, to understand that, you even need to go back a number of years, back to 1862, the Naval Act, creating land-grant colleges in the United States. So what this act did, Congress passed, basically said any state, or at least those states who were not in rebellion against the Union at the time, because this was during the Civil War, they said states could apply and the federal government would give them a chunk of federal land in the state in which they could build a university, or they could even sell that land and use the proceeds to start a university. And these schools should especially have work in agriculture and the mechanic arts. So the states took advantage of this. This is not a complete list, but the first was Kansas State in 1863. Some other schools, such as Penn State and Michigan, existed before that, but they were able to greatly expand using the land grant. In the case of Washington, it was Washington State University. That's the land grant college was, I believe, 1890. So here's a number of them. And then even MIT in 1865. Now, people think this is a little strange because MIT is a private university. But back at that time, there really wasn't the clear distinction that we have now between public and private universities. So MIT used land grant money to start in 1865. Cornell also used it. Another school we think of as a private school, but actually even to this day, Cornell has different components. I think even depending on your major may depend on your tuition, because part of it is considered a public university based on the land grant, and part of it is more of a private university. Now, Harvard and the other Ivy League schools were not land grant colleges, but they were changing as well. Up until the 1870s, students at Harvard and the other Ivy Leagues all took the same classes. But then they introduced an elective system in the 1870s, and that allowed students to start to specialize in science and later in engineering. So up until this time, most inventors didn't have a formal education, didn't read the scientific literature. There was a real disconnect. But starting in the early part of the 20th century especially, there's a stronger connection between science and engineering and education and inventors as well. So again, back to 1915, here's now page 6 of the New York Times. Edison has called for the creation of a great research laboratory jointly under military and civilian control. And at this time, as I mentioned, the war was going on in Europe, but we were not a part of it. There were some in the US who thought we could or would end up being in the war and wanted to have a draft. But that would have been very politically unpopular. There were others who wanted to totally stay out of the European war. But the Secretary of the Navy, Joseph Daniels, saw Edison's article, and he really liked the idea because he thought this was kind of a good middle approach, that we could at least create a laboratory to begin preparing ourselves on the technological side in case we did end up in this war or a future war. So he liked the idea. He met with Edison, and remarkably fast by government standards, just 6 weeks later, now it's page 1 of the New York Times, they announced the creation of this Navy test board that Edison will lead. And one of their main jobs was to create the laboratory that Edison had talked about. And most of the scientific and engineering societies were asked to provide 2 members, and you can see the members here. Not a very diverse group of people, but you can see Thomas Edison. You can see next to him is Miller Hutchinson, who was a prominent inventor in his own right. He actually worked for Edison at this time. And later, after Edison's death, Hutchinson would say the lab was actually his idea. And there's no proof of that. It very well could be true. I guess it's my view, somebody with Edison's stature probably has a lot of ideas thrown their way, and it's up to them to decide which ones to put forward. So regardless of whether it was really Hutchinson's idea, I think a fair amount of credit goes to Thomas Edison, because without his support for it, it never would have happened. And there's Joseph Daniels, the Secretary of the Navy. And here's Franklin Roosevelt, who at this point was Assistant Secretary of the Navy. This is before he had polio, and of course before he was president. So here's the societies that were included. Now, not included were the National Academy of Science and the American Physical Society. And that was at Edison's insistence. He didn't want them involved because he thought they just did a lot of basic research, which wouldn't be important for the Navy. And we'll come back to that in a minute as well. So it only took 6 weeks to create that board, but in the end, it ended up taking 8 years to actually create the laboratory. There were right off the bat disagreements within the board about where to put it. Edison wanted it in Sandy Hook, New Jersey. He said it was because it would be close to New York City, so it'd be easier to get employees and to get materials. But a lot of the other people felt he wanted it there just so it'd be close to him and he would micromanage it, which they didn't think would be a good idea. Some of the naval officers and others wanted to put it in Annapolis, Maryland or Washington, D.C. There was a question of who would be in charge. Would it be a civilian or military? And what kind of work would be done? Would it be what we think of as basic research or more developmental work? And as I mentioned, Edison had a pretty strong opinion on this. He said, I don't think scientific research to any great extent will be necessary. We've done work in every branch of science and industry, costing countless millions of dollars, and all this, very little of this has been applied and utilized. It goes on to say it's therefore useless to go up on piling up more data a great expensive delay while we are free to use this ocean of facts. So Edison, not a fan of basic research. And so now 4 years later, 1919, Edison is writing to the Secretary of the Navy and says, if naval officers are to be in control, the results will be zero. Goes on to say, if the great MIT with 3,000 students only produces one creative mind occasionally, how can one expect Annapolis, that is the Naval Academy, to produce any, especially as if one were produced, the naval system prevents it from being found out. So Edison seems to have a fairly low opinion of naval officers. And the reason may be that I mentioned that he created batteries that were used in submarines. So just a few years before this, the Navy was testing out a submarine in New York City Harbor, and they were using batteries, and there was a buildup of hydrogen gas. There was an explosion. 4 sailors died. And there was an inquiry, and Edison's company had provided the batteries. And Edison's company said, well, it wasn't our fault. We told them they needed to properly ventilate it, and they didn't. But there was a board of Navy officers that actually held hearings, and they concluded that Edison's company was at fault for this accident. So some believe that ever after that, then Edison really didn't care much for naval officers. That may explain what he's saying here. So that was 1919. Now, just a year later, we're now in November of 1920. This is right around the time of a presidential election. So President Wilson will be leaving office in a few months. President Harding will be coming in. Along with President Wilson, his entire cabinet, including Secretary Daniels, will leave office. So Daniels realizes if he's really going to get this lab going on his watch, he better do it now. So he decides to go ahead and put it in Washington, D.C. over Edison's objection. And he writes a letter to Edison here saying, partly explaining that one reason to put it in D.C. is that the government already owned the land, so they could actually use the money to build some things. And he goes on to say, I earnestly request your cooperation in carrying forward this original idea which you proposed at the first meeting of the Naval Consulting Board. So asking Edison to support it even though it's not in his preferred location. Edison writes back and says, no, I would prefer not to be connected in any way with this new experimental laboratory. So that's December of 1920. Administrations change, but plans for the lab go on. A couple years later, a naval officer writes to Edison again to ask if he would reconsider and be part of the new lab. And he replies and says, I'm not inclined to render any further aid as I think the present laboratory will be a sinkhole for money. So even without Edison's blessing, they go ahead and create it. And here it is, July of 1923 on the banks of the Potomac River, where it still is today. And now, I mentioned a few years ago, earlier, that the Assistant Secretary of the Navy was Franklin Roosevelt. Now it is Teddy Roosevelt Jr., who's the son of the late president. And in fact, Teddy Roosevelt Sr. had held this position back in the 1880s. And then in the 1930s, that same position, Assistant Secretary of the Navy, will be held by Charles Edison, the son of Thomas Edison. So it's kind of interesting how these names keep coming back. But anyway, Teddy Roosevelt Jr., when they commissioned NRL, said, I feel very strongly the Navy must not be allowed to petrify. We will petrify unless we are constantly reaching out for new and better things. And they started with just 2 divisions, sound and radio. Radio as a way to communicate with ships and submarines around the world, and sound especially as a way to detect submarines. And their focus was on high-frequency radio. U.S. industry was more focused on lower frequencies and trying to get radios into the millions of households. And so they really didn't have the interest or bandwidth to do research for the Navy, but they were willing to manufacture designs that NRL came up with. So places like RCA and Western Electric were manufacturing the NRL designs. And around this time, Navy engineers were transmitting radio waves across the Potomac, again, as a means of testing a means of communication. And a ship passed by and it interrupted their transmission. And they realized, this might be a useful thing. And they asked for additional funding, and that was denied. Now, that was 1922. Now, 8 years later, NRL's been around for a few years now. And they're using these high-frequency radio beams to guide planes as they're landing. And they notice an interference pattern or a Doppler effect when the planes would pass through the beams. Now, this was really not a surprise. By this point, quite a few physicists around the world understood Maxwell's equations. They realized there should be such an effect. The only question would be how strong would the reflections be, and would they be useful for anything or not? And what the NRL team found in 1930 was that the signal was very strong. And this time they initially were denied funding again, but they persisted and eventually obtained funding. Now, some historians believe that they'd gotten funding 8 years earlier, it might not have gone anywhere because the vacuum tubes hadn't been as well developed at that point. So a lot of these new technologies take several things coming together at the same time. And in 1930, it came together at NRL for the development of radar. So as I said, they obtained external funding so they could continue working on it, and the project was classified. But there was actually parallel work going on at Bell Labs, and I guess the Bell Labs people, nobody told them it was classified, so they, in March of 33, in what's the predecessor of the proceedings of the IEEE, they publish a paper in which they note they use radio waves to observe an airplane flying at 1,500 feet overhead. So at this point, the NRL engineers and scientists went to their management and said, well, it's not a secret anymore. Could you at least let us patent it? So they were allowed to do so. So in 1934, the first US patent on radar goes to people at NRL. Now this early radar was CW, or continuous wave radar, and it actually wasn't that useful. For example, you couldn't determine the direction from which echoes were coming. And a much better solution is pulse waves. So right from 1934 on, NRL began trying to work on pulse waves. They built in part on work they were doing studying the ionosphere. It's sort of the same physics, whether the EM wave is reflecting off the ionosphere or off a ship or an airplane. And they also brought some key ideas from the sonar program in NRL's sound division. And this is something that's happened many times over the years, is by having all these different laboratories in the same location, you get a lot of synergy that wouldn't happen if they were all isolated. So I think that's been very important for NRL's development. So by 1936, they demonstrated the pulsed wave radar. And by 1939, they put it on the first deployed ship, the USS New York, and the sailors like to refer to it as a flying bed spring. Now this is the 1930s. What else was going on? Well, there was a Great Depression around the world. And in 1933, Franklin Roosevelt became president, and he brought in, got Congress to pass the New Deal. So the federal government got involved in funding things they'd never funded before: roads, bridges, dams, what we call infrastructure today. Schools, my own kids went to a school in Arlington, Virginia, and in the lobby of it, there's a plaque that says built with WPA funds in 1939. Parks, they even paid artists to paint murals in post offices, some of which you can still see today. But one thing the federal government didn't do before or during the New Deal was fund scientific research. That was actually funded primarily by private foundations, the biggest being the Carnegie Institute of Washington, the Rockefeller Foundation, and the Ford Foundation. These foundations are all still around today, still funding research, but they're not as big a percentage of the overall funding as they were back in the 1930s, when there was no federal funding of research. At this point, I want to introduce Dr. Vannevar Bush. He grew up in New England, received a bachelor's and master's in math from Tufts. Years later, after he was well known, somebody went back and interviewed one of his math professors and asked if he was a good math student. And the professor said, well, he was quite capable, he said, but I wasn't overly impressed because the year before I'd had 12-year-old Norbert Wiener as one of my students. Anyway, after graduating, Bush spent about a year at the GE lab I showed you earlier, testing high voltage transformers. He taught math at Tufts for about a year, but decided he wanted to get a PhD. Didn't have a lot of money, so he needed a scholarship. He went to Clark University, and there was a well-respected engineering professor there who offered him a scholarship to work on an acoustics project. Bush said, no, thank you. I don't want to work on acoustics, and I don't like somebody telling me what I'm going to work on, so I'm not coming. He instead went and talked to MIT. They also offered him a scholarship. And he said, well, I'll come under one condition. That is that you promise that I can graduate in 1 year with my PhD. Well, MIT balked at first, but then he persisted. Eventually, they drew up a contract with him. They said, if you can do these certain things in this 1 year, you'll finish your PhD, and he did indeed do so. Now, I don't know if there's any undergraduates listening today, but if there are, even if you're a really good student, I personally wouldn't recommend you try this technique. I don't think you'll get any schools today who will promise to give you a PhD in 1 year, but Dr. Bush was able to do so back in 1916. So then he was an assistant professor of EE at Tufts for a few years, and then moved to MIT, where he stayed for many years, moved up the ranks, eventually becoming vice president at MIT. He definitely did not think of himself as a scientist or a mathematician, but definitely as an engineer, just as Edison would, and also as an inventor. So one of the problems with the early radios in households were they needed to be plugged into AC, but then they needed 2 different voltage DC batteries. So when one of those batteries failed, then people had to try to figure out what was wrong. It was not easy for most consumers. So Bush and some colleagues invented the S-tube for radios that allowed it to all be done just by AC power. And yeah, they created a company, the American Appliance Company, which then later changed its name to Raytheon, which is obviously still around today. Now Bush had, and then he also invented something called the differential analyzer, which is a machine for solving differential equations. And I'll show you a photograph of that a little bit later. And one of his graduate students, research assistants during this time, was Claude Shannon. And so Shannon wrote a master's thesis entitled a symbolic analysis of relay and switching circuits, which is, of course, the basis of our whole modern computers. And some would argue that was probably the most influential master's thesis in the history of the world. And Bush had pretty strong opinions about a lot of things and wasn't afraid to say them. So he thought that students were taught by a narrow specialist with an interest in the minutiae of a very limited field. The student is hounded, his hours are crowded and closely scheduled. He has little time for reading or reflection, and he does little such. All but the exceptional students become automatons. So now we're into the 1930s, and not only did Roosevelt come to power in 1933, but so did Adolf Hitler and the Nazis in Germany. And they began almost immediately violating World War I treaties that said they couldn't have a large military, especially started building up a large air force. Bush and others saw this happening, thought it could be a problem, thought we should be getting prepared. He wrote some editorials in newspapers about it, and people weren't paying too much attention. So then, even more than now, location really mattered. So Bush felt that if he was going to influence U.S. policy, he really needed to be in Washington, not in Boston. So he obtained a position as head of the Carnegie Institute. That's the largest of those private foundations I mentioned earlier. And they funded a wide range of physical and social sciences. Bush actually didn't care so much for the social sciences. He said that I have a great reservation about these studies where somebody goes out and interviews a bunch of people and reads a lot of stuff and writes a book and puts it on a shelf and nobody ever reads it. And in fact, he totally eliminated the Carnegie funding for archaeology. And some have argued that probably set American archaeology back by a generation. But later, in terms of what he went there for the technology side for the military, he said that I was located in Washington, I knew government and I knew the ropes. I could see that the United States was asleep on the technical end. So he got to know some of President Roosevelt's advisors, eventually got to meet with President Roosevelt himself, and convinced the president to sign an executive order creating the National Defense Research Committee in 1940 with Bush as its head. And we know executive orders are not permanent, so to get this on a more permanent basis, the following year, they eventually got Congress to create the Office of Scientific Research and Development, OSRD, and provide it substantial funding. And as head of this organization, he reported directly to President Roosevelt. Now, back in the First World War, scientists and engineers who wanted to help with the military effort were offered commissions in the military and then went and worked in military facilities. They were not funded to do work, for example, at universities. Bush was really adamant that it should be different this time. He felt the federal government should fund civilian scientists at the universities to do work that was important for the war effort. And there was some resistance from the military. In fact, the admiral who was the head of Naval Research Lab thought this was a bad idea. But Bush, was directly reported to the president, and he was able to win this battle. And so at its peak, OSRD was funding over 7,000 scientists and engineers, estimated about over 3/4 of the physicists, over half of the chemists in the United States were getting funding from this organization. And Bush had a lot of people to help him, but there was no way they could micromanage these 2,500 contracts. And so this has been sometimes called fruitful chaos, but it was chaos which helped win the war, as I'll talk about, and also helped lay the foundation for the great technological and industrial expansion in the US after the war. So I was talking about the US. Now, the UK also saw Germany's buildup in the 1930s, and they didn't have the Atlantic Ocean protecting them. All they had was the English Channel. So many people there were very concerned, and they were especially concerned about aerial bombardment because they had no defense against it. So they created a committee in 1934. It was led by Dr. Henry Tizard, and he was a chemist who came up with the octane ratings we still use today. He was also a test pilot with the RAF in the First World War, so he had a lot of experience that was relevant to this. And under his leadership, they developed a land-based radar system and demonstrated it in 1937. Now, this is all kept very secret. The people at NRL, I think, had some inkling that there was maybe some radar work going on in the UK and vice versa, but there was not any collaboration at all going on at this time. So that was 1937 when they demonstrated their land-based radar. From the beginning, the UK exempted all scientists and engineers from the drafts. They could work on things like radar. That did not happen in the US, so a lot of high-level people, including Bush, had to spend quite a bit of his time writing individual letters, getting people, scientists and engineers, not to be drafted so they could continue doing the research and engineering for the war effort. And some of you may have seen a good movie a few years ago about this, that the British not only mobilized the scientific community, but they went out and recruited crossword puzzle aficionados and chess masters who then broke the codes at Bletchley Park, and this was almost all women that did that work because the men were off fighting in many cases. And so the Battle of Britain began in June of 1940. This was aerial bombardment by Germany. The plan was for a few weeks or months of bombardment followed by an invasion. But what Germany didn't know was that the British had radar. They were able to see the German planes soon after they took off from Germany, scramble their RAF jets and engage them, and eventually ended up winning that battle. Again, a lot of historians believe if it weren't for radar, there's a very good chance that Britain would have ended up losing that battle and being invaded and surrendering at that time. So during this time, the British had come up with a number of inventions that they thought would be very useful for the military. But the problem was they were under embargo, they were under a bombardment. It was very hard for them to manufacture things. So they had the idea of sending these blueprints or prototypes to the US to share with us, hoping that we would share some of our military secrets with them, but maybe more importantly, that we would have our industrial base to produce these devices. Again, the US was not in the war at this time, and there had been some sharing of information in the First World War, but not since then. Now, there was arguments in Britain against this mission because they said, well, you'll be giving away our great technological advances to the Americans, and after the war's over, they'll take advantage of it economically. And Churchill eventually said, well, that may be true, but if we lose the war, that really won't matter. So he authorized a mission led by Dr. Tizard to bring these inventions to the US. They put them all in a big metal box, brought it across. There were prototypes in there. There were blueprints for things like jet engines in there. And they brought it and they met with people in Canada and the US, including Dr. Bush, including people from Naval Research Lab. And one of the problems they had back then was on radar, their land-based radar successfully worked, and it had wavelengths of many meters or even kilometers. But if you want to put a radar on a ship or an airplane, you need a much shorter wavelength. And the problem was there was no good sources of these short wavelengths. But just a few months before this mission, physicists at the University of Birmingham had developed a cavity magnetron, and they brought one with them to demonstrate to the US, and it was emitted at 10 centimeters, and it had 1,000 times stronger radiation than anything the US had at that wavelength range. And there was also information that got transferred the other way. NRL, for example, had developed a duplexing so they could do transmit and receive off the same antenna, so that information was transferred to the UK. This magnetron is in all of our microwave ovens today, and it's been called the most valuable import in US history. It was also pretty amazing. From the time they demonstrated that to the time AT&T was producing it was about 7 weeks, which is, to me, pretty amazing considering how long it takes something like that to happen today. Now, when the UK team came over and the US started interacting with them, they realized that the UK had about 2,000 people working on radar, and the US had a couple dozen people at NRL. So Dr. Bush and others realized we really need to ramp that up. They did ramp up some at NRL, but there was only so much space, and they were also subject to civil service hiring rules, so they couldn't ramp up that quickly there, fully ramp up. So Dr. Bush had the idea of creating what became called the MIT Radiation Lab, and they brought scientists and engineers, about 2,000 from all over the country, to work there on radar and other things for the war effort. So then there was a lot of transfer back and forth during the war between the US and the UK. And in fact, the MIT Radiation Lab decided to create a branch office in the UK in Malvern to help facilitate this transfer. To head that office, they selected a well-known electrical engineering professor and physicist named Dr. John Trump. And he then headed that office in Malvern for a couple of years during the war. Now, I've got a quote here from one of Dr. Trump's relatives. I think it was from last year. He said, quote, he's talking about climate change. He said, "You have scientists on both sides of it. My uncle was a great professor at MIT for many years, Dr. John Trump, and I didn't talk to him about this particular subject, but I have a natural instinct for science." So you can guess who might have said that. So in addition to the battle for Britain, there was the battle for the Atlantic. So once France and some of the other countries fell, Britain was isolated in Europe. They were under embargo. So the only way they could survive was for the US to send massive amounts of food, fuel, and munitions using merchant ships. So then Germany, using their submarines, their U-boats, began sinking these ships. And overall, the numbers were pretty staggering. During the Atlantic War, 7,400 merchant ships were sunk, almost 200 British and US Navy ships, and almost 800 German U-boats were sunk by the Allies. So numbers are pretty staggering. About 20,000 men were lost on both sides. Those numbers are large, but compared to the Army losses, they're relatively small. So it wasn't really a matter of getting more sailors out there, but it was a matter of how quickly could we build the ships how quickly could they build the U-boats? How quickly could we sink the U-boats? And how quickly could they sink the ships? So it really became a matter of numbers. If you could just shift things by a few percent one way or the other, you could win this battle. So there was really enough data to get some good statistics and apply mathematics. So they put scientists and engineers on some of the ships and airplanes to help collect data, and they developed a whole new techniques of analyzing this data. And this became what we now call the field of operations research. And in particular, Peter Blackett from the UK, Naval, those of you in semiconductors probably heard that name, as well as Philip Morse. Some of you in physics might have, I think these people still use a classic textbook by Morse and Feshbach on graduate level physics. Anyway, these were the three of the key people who helped develop this field of operations research during the battle for the Atlantic. And so based on applying these statistical techniques, they would come up with recommendations, some of which were intuitive and some were not. For example, planes, when they're hunting submarines, should always fly below 2,000 feet. Radar operators had to have frequent breaks or they became less efficient. And once a submarine had been submerged for over 2 minutes, don't drop a bomb on it. It's not that it might not sometimes damage a submarine, but just statistically speaking, you're better off to save that bomb to use another time on a submarine which had not been submerged for as long. So by applying these mathematical techniques, applying these mathematical techniques, they were able to shift things enough to where we were able to, basically sink the U-boats faster than they could manufacture them. And then in 1943, a couple years before the war came to an end, Germany pulled all its U-boats from the Atlantic, and the German commander at the time stated that it was not superior tactics or strategy, but superiority in the field of science that caused them to lose that battle. And I mentioned earlier that Dr. Bush created this differential analyzer. So here's a photograph of in the US of young women using these to solve differential equations to calculate shell trajectories for the Army. And Dr. Bush didn't like the social sciences, but his organization actually did end up funding some social sciences, in particular in psychology. So back in the 1940s, most young men had very little expertise in technology. I mean, some of them had radios at home they tinkered with, but other than that, very little. So you put them on these chips with a lot of complex systems. A lot of them didn't know what to do. It was a real problem. And so what they did, they brought in a team of psychologists for the battleship New Jersey, which hadn't been commissioned yet. And they developed tests and training to figure out which crew members should do what job and how to train them to do it. And the result was very encouraging, much more efficient crew, better shakedown crews. And some other Navy captains, when they first heard about the psychologists, thought it was all pretty silly. Once they saw the results in the New Jersey, they wanted the psychologists to come and do the same thing on their ships as well. So it was very beneficial to the Navy. It was also beneficial to the field of psychology because you had this captive audience of thousands of crew members who were required to take your tests. And so they were able to develop new techniques in psychology by doing this. And I mentioned that Dr. Bush said that they should fund researchers at the universities, and they did that during the war. And I just want to mention a couple that I thought were interesting. One was Doc Edgerton, inventor of the stroboscopic photography. There's a classic picture you might have seen of the bullet going through the apple. I actually had when I was at MIT, he was still alive, and I actually got to hear him give some very good lectures at that point. But anyway, during the war, he was under contract with the Army and developed flash and high-speed photography to do night photography, in particular over France before the Normandy invasion. So that was crucial for the Allied effort there. Another, also from MIT, was Charles Stark Draper, who developed better techniques, for example, to shoot down airplanes and the German V-1 rockets. And the final person I want to mention is Luis Alvarez. He'd gotten his PhD at Chicago in 1936, worked in the radiation lab at Berkeley, working on nuclear work in the late 1930s, for example, measure the magnetic moment of the neutron. And then he was one of many of the top scientists who was recruited to the MIT Radiation Laboratory in 1940. There he began working on radar. He developed a microwave early warning radar. This is the first time anybody used a phased array technique in radar. He also invented something that was really critical, ground-controlled approach radar. Before that, pilots really could not land at night or in bad weather, and this enabled them to do so. And what he invented was used for many years during and after the war. And then, like some of the other radiation lab scientists, he was actually then recruited to the Manhattan Project, where he spent the last year or two of the war, did a number of things there, including developing a way to detect radioactive gases to look for nuclear reactions. So this was actually something that was then used a lot during the Cold War, when both the US and Soviet Union were doing nuclear tests in the atmosphere. Now, many of us work to get a PhD in a field and work and hopefully try to make a contribution in that field. What amazes me about people like Alvarez is his ability to switch from one field to another and make incredible contributions. And in fact, then in 1980, I was in high school and got to go to a AAAS meeting, and he talked to some of the young students, including myself, and he was talking about a paper he and his son, a geologist, had just published, arguing that the extinction of the dinosaurs 65 million years ago was due to an asteroid impact. And at the time, it was fairly controversial. Since then, I think it's become more accepted. But anyway, his ability to switch from one field to another makes such a contribution. I think it's really amazing. And I think that showed Dr. Bush's wisdom in realizing you want to engage people like that at the universities in the war effort. And then when D-Day came, Germany had a lot of advantages. They were entrenched in the French coast. They had bigger and better tanks, and I think more of them than the Allies did. But the Allies really used a whole range of disciplines, better meteorological predictions. They used the operations and research analysis. They had the radar. They even employed magicians to make it look like there was a whole phantom army in the north in Scotland that Germany thought was going to invade somewhere to the north. So they thought this first invasion was just a fake. So not just a D-Day, but in the war as a whole, the Allies did a much better job of combining information analytical techniques from all these different disciplines and applying them in the war effort. So, been a little long diversion into World War II. What's this have to do with O&R? Well, later in his biography, Bush said, if we'd been on our toes in war technology 10 years ago, we probably would not have had this damn war. So he's basically saying, going into the future, we don't want to let that happen again. And so late 1944, here's a letter from President Roosevelt to Dr. Bush asking him to come up with a framework for how the federal government should continue supporting research for military and other applications after the war. It turns out this letter was actually written by Dr. Bush. He sent it to Roosevelt's aides. They made a couple changes, and then Roosevelt signed it, sent it to Bush. And of course, Bush was happy to oblige. He quickly put together some committees. They looked into these issues. And the following year, they issued a 100-page report called The Endless Frontier. In that, he argues for government accepting responsibility for promoting the flow of new scientific knowledge. And it's kind of interesting because Bush was a staunch Republican. He hated the New Deal. He thought the federal government shouldn't be involved in all these other activities, but he made an exception for scientific research. He thought there was an important role for the federal government there. He also argued for plenty of men and women trained in science. I thought that was significant, that back then about only 1% of American scientists and engineers were women. And so it was interesting that he included that in the report. And arguing that basic research especially would be done at universities and research institutes, and realizing that it's a long-term process. And then he called for the creation of what he called the National Research Foundation. And the chart is shown here. Now, for those of you who are not old enough to remember, this is an example of how you can make an organizational chart using a typewriter. But anyway, he called for all the different types of research to be under one umbrella. That's, of course, not the way it turned out. Instead, we have the National Institutes of Health, we have the National Science Foundation, and then we have the different DOD and Department of Energy efforts as well to fund scientific research. And in fact, there was a big fight in Congress over this when Bush and others proposed it after the war. I think the senator from West Virginia said, oh, I can imagine all the funding is just going to go to Massachusetts and California. Some argued that public should own the patents since they were paying for the research. Others argued that they should use the same research techniques that won the war to solve social problems such as hunger and homelessness. And there was a big question of who would be in charge. Would it be a director appointed by the president, or more of a board of scientific experts who are not political? And in the end, because of this fighting, it took them, it wasn't until 1950 that NSF was created, and they really didn't get much funding until the late 1950s. But the Navy didn't wait for that. So beginning in May of 1945, before the war was even over, the Secretary of the Navy created the Office of Research and Inventions with the idea of being able to continue federal funding of research at the universities after the war. But most of the universities just assumed it would go back to the way it had always been before the war, which is no federal funding. And they were concerned that here's an article quoting the president of Yale saying, no, we don't want the federal government taking over the universities. They'll be classifying things. It won't be good for academic freedom. It'll be a disaster. And yeah, here's some of their concerns. But the Navy turned around and said, no, we will let the scientists choose the projects and realize that all basic research has potential naval applications. The research would be unclassified. We would even pay overhead costs, and only annual reports would be required. And in fact, the early contracts to the universities were one page, a little bit different than it is today for those of you who have submitted grant proposals to O&R or other places. So they agreed on all these things, pretty much everything the universities wanted. And then they even had to set up a team of Navy people to go out to the universities to convince them to continue accepting federal funds after the war ended. And once some of the universities said yes, it was kind of hard for the others to say no. And because there were a number of years where O&R was the only funding game in town, Newsweek called O&R the Santa Claus of the basic physical sciences. So in August of '46, O&R was created to plan, foster, and encourage scientific research in recognition of its paramount importance as related to the maintenance of future naval power and the preservation of national security. So this was a big change. Never before had there been peacetime funding of research by the federal government. And then in '47, when they were again still trying to create NSF, some people said, well, once NSF is created, we'll transfer all the basic research from O&R to NSF. But the Secretary of the Navy argued that would be disastrous. He said, our experience has been unless the Navy is in direct contact with the men actually conducting the research, they cannot successfully and quickly work out the practical applications. So that is in some sense why still today, O&R funds not only the more applied work, but also the basic work. So one area in which Germany was well ahead of the Allies in the war was in rocketry, and they developed these V1 and V2 rockets. So at the end of the war, about 100 of these rockets were brought to the US. Some of them were given to the Naval Research Lab, and they took great advantage of them. They never, at this point, no one had ever done any scientific measurements beyond the atmosphere. So they were able to launch these rockets and do things such as UV and X-ray radiation measurements. So it was a great scientific boon for the Naval Research Laboratory. And at this point, they began also thinking about trying to put a man-made satellite in orbit. And working toward that, they developed a tracking system. They thought they were going to use it on their own satellite first, but instead the Soviet Union surprised everyone by launching Sputnik in October of '57. But the US tracking system worked quite well on Sputnik. And then just a few months later, NRL launched its first satellite. It was the first use of solar power, and that satellite is still in orbit today. And then the following year, the first weather recording satellite. And then in 1960, what turned out to be one of the first spy satellite was launched. Now, after Sputnik in 1957, people were very concerned that we were behind. So that led to the creation of DARPA in 1958, and also the creation of NASA in 1958. So almost all the NRL people with the space expertise were transferred to NASA. But NRL decided they wanted to maintain a presence in that area, so they hired new people. And to this day, they still have a very strong space program. They don't do launches themselves, but they certainly build satellites and do scientific experiments in space. And here is an example from early 1972. Dr. Carruthers from NRL demonstrating a UV camera to the astronauts of Apollo 16, and they then took it on that mission and were able to do the first images of Earth and other celestial objects in the UV. And here is Dr. Carruthers many years later receiving the National Medal of Technology from President Obama. Now, going back to this plot of the multiple receivers to pinpoint the location of the satellite, Mr. Easton, who is the author of this paper, he and others had the idea that, well, you could invert this process. Instead of having multiple receivers on the Earth and one satellite, you could have multiple satellites and one receiver on Earth whose location you wanted to find. That then is the basis of our GPS. And Easton's key ideas included putting atomic clocks on the satellites because timing is critical in GPS. Things are traveling at the speed of light. And so then in the late 60s and early 70s, under his leadership, NRL put up 4 satellites, a couple with atomic clocks, and demonstrated the GPS concept. And it's interesting, so now this is about, 60 years after Einstein's theory of general relativity was published. This is the first practical use of general relativity, is in GPS. And if they didn't have those corrections, GPS would not be nearly as accurate as it is. And then here is Mr. Easton receiving Medal of Technology from President Bush. And also in 1970s and 80s and beyond, O&R was funding Dr. Phillips at NIST, and he did work on laser cooling and atomic fountains. So accuracy even better than the atomic clocks, so 1 part in 10 to the 16. So those clocks are, for example, used in the master clock in the Naval Observatory to control the entire GPS system. So I mentioned earlier Dr. Alvarez's idea of phased array radar, and one problem with that is you need power amplifiers for each element. So that's an area in which NRL and O&R both had important roles to play. Back in the 1970s, NRL developed Joukowsky growth of compound semiconductors such as gallium arsenide. So that technique then got transferred to industry, and now it's used worldwide. In the 70s and 80s, O&R funded a lot of 3.5 material and device work, which then ultimately by the 1990s gallium arsenide-based phased array radars were developed by Raytheon and others and used in US Navy ships. Now, if you take a look at the band diagram, band gap versus lattice constant, you see gallium arsenide here, you see the nitride family here. And so starting in the 1980s, when nitride materials started to get a little bit better, the Navy and DoD in general realized there was really no good reason for the US, for the government to be involved in the LED side of this, because the commercial industry would take care of that, and indeed they have. So where they put investments was more in the wide bandgap power electronics for radar based on gallium nitride. So that's been a success story. So now there are still gallium arsenide based radars on the Navy and DoD uses, but now there's also gallium nitride based electronics for radar and other high power needs. So NRL today, still in the same location on the banks of the Potomac River, over 2,000 people. Instead of 2 divisions, we now have 18 divisions. I'm not going to go through all of them, but for example, the division I spent my time in was electronic science and technology. Almost everything we did there was unclassified and we published in the open literature. On the other hand, there's the tactical electronic warfare division. I'm not even allowed in their building. They have no windows. Almost everything they do is classified. So NRL has a mixture, and I think it's the strength of NRL of both basic work and the more applied, and in some cases, classified work for the military. And here's just a list of some of the NRL accomplishments. Some of those I talked about, some others I didn't have time to talk about. And that's the unclassified list. I'm sure there's a similar classified list somewhere. And NRL today, if any of you are students or have students might be interested, we have programs, high school programs for summer students. We bring in undergraduates and graduates in the summer as well. We have an internship program, a postdoc program. That's how I ended up at NRL initially, as well as a faculty summer and sabbatical leave programs. ONR today, a budget of over $2 billion. We fund both basic and applied research. And there's always been this recurring tension over what research ONR should fund and what's truly basic and why should ONR do it versus NSF, for example. And back in the early 70s, some students at Stanford, I'm not sure exactly how they did this, but they got a hold of some internal ONR documents, and they found that the grants to universities all had 2 names. One was a name given it by the PI, which in this case was high power, broadly tunable laser action in the UV spectrum. But then there was an internal name ONR used so they could convince their Navy sponsors that this was important for the Navy. So in this case, the title was Weaponry, Lasers for Increased Damage Effectiveness. So they published this in science magazines. Some of the faculty members were sort of embarrassed and said, no, I'm not really working on military work. I'm really just doing basic research. And so today we have grants for single investigators, multi-university research initiatives, young investigator program, a small business program. In many cases, universities can be part of these small business grants, special grants for HBCUs. And we also, DoD-wide has the Vannevar Bush Fellowships, which is for senior faculty members. It's a total of $3 million over 5 years. Now, I mentioned that TZARD mission, how important that was with the cooperation between the US and UK. And so I think partly because of that, they created what's called ONR Global, which is headquartered in London, but with offices in Europe and Asia, as well as South America. And they keep abreast of research going on around the world and actually fund projects around the world. In many cases, they're people, in some cases, doing collaborations with people in the US, but not always. And they fund not only traditional allies like the UK or Japan or Australia, but they also fund other countries such as Vietnam that are not exactly allies, but it's also seen as a way to obtain better relations with these countries. And also with some of the developing countries, money can go a long way. A $40,000 grant can buy more in a place like Vietnam than it can, for example, in the United States. And so today I tell people my job is to fund people with creative ideas of how to use the periodic table to ensure the Department of Defense dominates in the electromagnetic spectrum. Back in the Second World War, it was primarily radar, but now it's a whole range of different EM wavelengths that are important for the Navy. So I mentioned in 1922, Edison wrote that, a couple of those kind of nasty letters saying he didn't want anything to do with NRL. But after it was created and he saw what had happened, he actually changed his mind and decided it would turn out well after all. He actually sent the letter may be lost to history, but I've seen it referred to a couple times, but he sent a letter to NRL, including a signed photograph of himself, saying that he was happy with the way it turned out. Dr. Bush stayed at the Carnegie Institute till the mid-1950s and then returned to MIT as an emeritus professor. And Dr. TZARD, after the Second World War ended, during the early parts of the Cold War, there were a lot of sightings of UFOs, and a lot of people just said it was kind of silly and dismissed it. But Dr. Tizard said, well, we really ought to take a serious look at this. So a committee was created that he headed, and I love the name of this is official, committee of the British government. I love it. It's called the Flying Saucer Working Party. And they did a report, which was actually not declassified until 2001 for some reason. And it's hard to prove a negative, but they basically didn't, they found explanations for some of the things and didn't find any evidence of aliens among us. So I want to conclude, well, was Edison's vision for NRL fulfilled? Well, I personally think if they'd only done the applied work like he talked about, it would not have been nearly as successful. So I really believe the mixture of a basic and applied research is really what's made NRL a success over this almost 100 years now. And as I mentioned, ONR was initially the only place doing federal funding, so they really set the standards for how federal funding of university research would be done. And so Dr. Killian, who was president of MIT and later President Eisenhower's science advisor, said, ONR represents an extraordinary achievement in successful and enlightened government management of research. So with that, I will conclude and be happy to answer any questions. Thank you.
A fantastic talk about the history of scientific research organizations. If you have any, for the audience, if you have any questions, you can type in the chat or maybe just unmute yourself and ask a question. While we are waiting, I have a quick question.
Sure.
So even in the military, we have ONR, we also have Army research and Air Force research. So how does these military research branches coordinate their effort and also any competition in between?
Right. Yeah, it's a mixture, and obviously there is some overlap. All the services certainly need, good electronics and good imaging and things like that. So we certainly try to coordinate some, especially with efforts like MURIs, where we intentionally get reviewers from the other services. But I think there's some advantage to having, in some sense, some competition. I think after the war, when they set up the DOE, what are now the DOE laboratories to do nuclear research, they purposely set up competition in some ways between some of those laboratories to make sure that the best ideas didn't get forgotten. So I think it's somewhat similar with the different services, but we certainly do coordinate a fair amount between the services. And there's certainly some things such as oceanography and things where it's pretty clear that the Navy should be the one doing it, but there's other areas where there's definitely overlap. And sometimes if someone comes to me with an idea that I think is really good, but I don't currently have funding, or I'm not funding someone in that area, then I would refer them to somebody at the Army Research Office or AFOSR, for example.
Great.
Let's see. I guess I'm not seeing the chats. So if you want to just maybe read any other questions to me, that would be.
Yeah, I have a question. I could not raise hand. I think as I'm co-host, so this is Arka.
Okay.
Yeah. So one thing that from this history, it seems like there were the Bell Labs, Edison Lab. Those were extremely prolific and created the history of science. But we don't really have I don't think NRL reached that stature, probably because NRL doesn't have maybe a money stream. I don't know. What's your opinion on that? Why we don't have Bell Labs kind of organization anymore?
Right. Yeah. Bell Labs had that advantage of, for however many years they got, I don't know what it was, 1% of AT&T's profits, and AT&T had a monopoly on phone service for the whole country. So they had this stream of money, which they really devoted to basic research. But of course that dried up when AT&T was split up. And what interesting thing there is, if you look at the federal budget, you will not find NRL listed. NRL does get one chunk of about a quarter of its money directly from ONR, and that they're allowed to decide how to spend. But the rest of their funding, they actually have to go out to the different agencies, mostly the federal government. But actually, when I was at NRL, I actually had funding from Intel at one point. So it's possible even to have private funding into NRL. And that has its pluses and minuses. It means, just as you guys have to do at universities, a lot of the scientists and engineers in NRL have to spend a fair amount of their time trying to find funding. But it also, I think, helps keep NRL relevant to have to do that if they didn't. Although Bell Labs was certainly very successful, where they didn't have to go for funding. But I think that's, like I say, it's both a plus and a minus for NRL.
Brian, we have a question in the chat from the audience. He's asking, where do you see the future of technologies such as RF antenna, wireless communication? It's kind of broad question.
Yeah, I mean, I'm probably a lot of other people are much more expert in, looking at the future for that. But one thing I will say is that one thing that's changed a lot is there was much of the time in the, 1950s, 60s, and 70s where the Department of Defense was really leading the way in a lot of these microelectronic technologies, and as well as places like NASA. And that certainly has changed over the years. So now, with obviously companies like Intel, and of course with smartphones and the World Wide Web, that the commercial market just overwhelms anything that the military is going to do. So our mode of operations change a little bit. So in some cases, we want to follow along what's going on with the industry, and then try to identify certain niches that might be appropriate for the military, and then pursue those, but no longer leading the whole microelectronics as was happening for many years after the war.
Yeah, he says, thank you. So I have a quick question again. So you show the periodic table. There are only 200 elements on that table, right? So so how far? I mean, what are the chances we find the new materials, right, for EM? And should we instead focusing on improve the quality and hybrid combination, or we really should looking for a new compound semiconductor and other materials?
Right. Well, I think there are, like I say, there are only so many elements and so many compounds, but then as you get into these structures and meta surfaces and other things, there are almost more than you can more possibilities than you can test. So I think one of the things going forward now is doing more supercomputer modeling of these materials and predictions, so that we can figure out which material, not only materials, but what geometric configurations will provide the best output. And I think really take advantage of things like machine learning going into the future. I think that's going to be key to utilizing, because you can't test everything, and it's gotten to the point too. Some of these say photonic structures and things. There was a time where a lot of them, designers could just use some intuition and figure out what might work and try it out. But now some of them have gotten so complex, I think they defy intuition for most everybody, and it becomes really crucial to have software that can find optimum solutions and optimum materials combinations, more so than it would have been, say, 20 or 30 years ago.
Great. From the audience, are there any other questions? Okay, then we should probably stop now. I'd like to represent the whole department. Thank you again for the fantastic talk.
Okay, thanks. I very much enjoyed it.
All right, thank you very much.